Before there was broadband internet, before there existed billions of websites, people were using their computers to go online. In the 80s and 90s, information services like CompuServe, Prodigy, Videotex, and thousands of bulletin board services were the internet. Computer users went online to access these information services using a phone line and a modem. In this video, I'll describe a modem I built for the 8080 computer that uses the best networking technology of today to access information services from the past that still operate today. My latest project for the 8080 computer is a Wi-Fi modem. This is the schematic for my 8080 Wi-Fi modem. On the left are the pins from the ESP32 DevC module and the pins for the RS232 TTL module. To keep space to a minimum, I decided not to install a header socket for the ESP module. Instead, I inserted the module directly on the proto board and soldered wiring directly to the ESP32 DevC module header pins. I've numbered the pins similar to the way an IC is numbered, with one starting in the upper left, incrementing down the left side. Pin 20 starts at the lower right, incrementing up the right side to pin 38 at the upper right. The RS232 to TTL module is from Amazon and includes a MAX 3232 transceiver chip that operates between 3 volts and 5 volts. I've mounted that module on the proto board so that the connector extends out the back of the modem case. Only the TX and RX signals are used on the module, which means, unfortunately, that half the MAX 3232 chip is unused. I decided not to implement hardware status and handshaking on this version of the Wi-Fi modem. It's receive and transmit only. All signal and status lines are buffered by a CD4050 hex buffer chip that provides about 18 milliamps active load drive for the LEDs. In addition to being attached to UART2 on the ESP32 module, are connected to a CD4098 dual monostable chip. I use this to lengthen the RX and TX pulses so that the front panel LEDs can be seen blinking at higher rates. When you get to around 9600 baud and higher, the pulses are so short that the LEDs are mostly dark. The 4098 takes care of that. The CD series chips, CMOS chips, will operate normally down to 3 volts, still have good noise margin and switching rates, and input currents are mostly negligible. Everything on the modem board is powered by the ESP32 module. I'm using the USB-C port on the module to power the modem, and then I just take off the 3.3 volts on pin 1, and I feed that to everything else on the modem board. I'm using ZI modem from Bo Zimmerman on the ESP32 module. His implementation has a very complete Hayes AT command set, and it's very easy to adapt his code for the ESP module you have. There are 2 files that require some adjusting, zimodem.ino and pet2asc.h. All of the changes I made were to specify which GPI ports to use and which UART to use as the command data interface. I'll show you that. So this is zmodem.ino, and I made some changes down here to define which pins I'm going to use. So I made some changes here for the auto answer pin, the high speed pin, and the Wi-Fi LED pin. I actually didn't end up using the HS pin. I skipped that one just to keep the number of LEDs down. Then a little lower here as well, I specified some additional pins that were needed for some of the signal lines I wanted to bring out. So this is really it. I mean, you can in his software, you can change whether the signal lines are active high or active low, whether they're used at all. or which GPIO you want to use for a given signal line. So it was really easy to adjust to get mine to work. pet2asc.h is where I defined I'm going to be using UART number 2 as the main UART, the command and data interface, whereas my debug UART is UART number 0, and that's the one that's attached to the USB-C port. So I just changed these equates right here, and that worked perfectly. It's started up and ran the first time once I compiled the code and loaded it into the module. So that's really all you need to do. I've placed the source code that I modified, a complete package, on my website. But you can find Bo Zimmerman's original source code on his GitHub page, which I have displayed here. So definitely take a look at this source code. I think it's an example of some well-written software for ESP32. Explains a lot on how you can use an ESP32 to do something like this. Building the modem involved gathering up the parts that I needed according to the schematic, like the LEDs and some resistors. I got a gray cabinet from Amazon, very small. It's actually very light, but the plastic's really easy to work with. So I took a piece of vector board. This is where I've mounted the RS-232 module, so it's mounted with the DB9 connector poking out the back. And there's my ESP32 module. I've got a hole cut for the USB-C interface. And I'm using a Dremel tool to cut some small holes. I also used an upright drill press to cut the holes for the LED. So I started building this board, and for some reason I put 2 sockets in here for the LED drivers, and I don't know why I did that. So I took it off and pulled some of the wiring out so that I just have 1 socket here for the hex buffer, and this is the socket for the dual monostable. And here it is corrected. So now I've got a single socket for the hex driver. And I epoxied the LEDs in place just to make sure they don't move around. But everything else is now mounted to the board. The ESP module is inserted into this perf board, and the connections are soldered to the back. But I did use a cable with a set of header pins to connect to this RS-232 module. So here's the board mounted in the case. When I was cutting the holes for the LED, I didn't have the plastic secured to the drill press, and so twice my drill got away from me and cut the hole a little weird. But the rest of them turned out good. So that was just a learning experience on me that even if it's plastic, you do need to clamp it down so it stays put. Otherwise, you're going to get elongated holes like I did. But it actually looks really nice installed in the case, and I've got a set of screws that screw this perf board down, and there are some standoffs underneath that to give it some elevation. And this is the modem without the back panel installed. You can see the DB9 on the back here. That's where I'm going to connect this to the 8080 computer. And this USB-C port on the side is really just used to power the modem. It doesn't do anything else. So I'm just running this cable directly to a wall-mounted power supply, just a wall-work power supply. And there's the modem assembled with the case on the top. And there's the modem from the back. Decent appearance. I was thinking about painting this case, and I'm still going to do that, but for right now I'm just leaving it the color that it came to me. And this is what it looks like attached to the 8080 computer. I'm going to do a demonstration on this in a minute. The first step in this demo is to get the new Wi-Fi modem attached to the 8080 computer. This is the serial cable that connects the modem to the computer. The far end is attached to the computer's serial port. The near end is attached to a DB9 to RJ45 cable adapter. This is the USB cable that connects to a 5-volt power adapter and delivers power to the modem. First, I'm going to attach the power cable and power up the modem. Next, I'm going to attach the serial cable. Now that the modem's attached to the computer, it's time to test for connectivity and then configure the connection to the Wi-Fi network. First, I'm going to run the Kermit program, and then I'm going to connect to the modem using the connect command. After that, just type in AT, and if you get an OK, you know the modem's working. I'm going to configure the modem first using the AT plus config command. That allows me to set the host name, the Wi-Fi AP name, and a number of other parameters in order to get the modem working. Once everything's configured, I'm going to save the configuration, and then I'm ready to connect. You'll notice that the Wi-Fi light is on. That means it's connected to the Wi-Fi network. To demonstrate connecting to a service out on the internet, I'm going to use the Kermit program on my 8080 computer. I'm going to execute the connect command to connect to the modem, then run the AT command to verify that the modem is communicating. Then I'm going to establish an outbound telnet connection to kermit.quux.org. This is one of the last, or the last, Kermit server out on the internet. I log in with an anonymous username, and anything is the password. Kermit was a file transfer application, and Kermit servers were file repositories. So you could connect to a Kermit server, you can change directories similar to FTP, and you could upload and download files. To disconnect from the Kermit service, I'm just going to press the Hayes +++ command. That returns me to command mode for the modem, and an ATH hangs up the connection. And from here, I can exit back to Kermit, and then exit Kermit back to CPM. Next, I want to connect to a BBS, a bulletin board service. These were the websites of the 80s and 90s, actually. Log into Kermit and run the connect command. Now I want to connect to vintagecomputing.com. Vintagecomputing.com is the home of the Cave BBS, one of the most popular BBS services in the 80s. Splash screen, some information, and I'm on the main menu. Now notice that I forgot to turn on flow control, so that's going to give me some odd characters every now and then. One of the nice features of a bulletin board service was electronic mail. I'm going to log off. That disconnects my connection. Exit back to Kermit, and then exit back to CPM. Here's another BBS service on the internet. It's running the Synchronet BBS application. You notice these are very colorful, but they're all text-oriented and menu-driven. Well, hopefully that's given you an idea of how this Wi-Fi modem works and how you can use it to connect to services on the internet.